Hello, my name is Trevor Appler, and this is my final video project for the University of Maryland Mechanical Engineering Remote Sensing course, designed and taught by Dr. Mitchell. The course not only teaches about a really cool real-world remote sensing application, but it also offers a sweet, on-a-budget, hands-on experience, which is the kind of thing that drew me into engineering in the first place. The idea is simple, but the application is not. The challenge was to find an icon on campus and to generate a 3D representation of that icon with nothing more than yourself and your homemade LiDAR device. Some LiDAR systems are built to interpret entire environments with great detail and precision. My goal for this project was simply to convince an observer that my point cloud and icon are one and the same. Originally, I chose my object by Ludwig Field in the Friendship Garden. The sculpture is really cool with a lot of unique features. The problem was when it's 3 in the morning, the lots are empty, and a car parks right next to yours, you're not going to want to ever come back. So I scurried off, and I found a new spot right by Oakland Hall on North Campus instead. Some cons were that the Wi-Fi connection was bad and there was a lot more lighting than I would have hoped, but I really liked the object for the unique features such as the door, the overhanging roof, and the post. The LiDAR setup that I used is standard to the one that Dr. Mitchell designed. It consists of a 3D printed mount with an Arduino at the bottom powering the red line laser transmitter and a receiver at the top powered by the Raspberry Pi, the same computer that is also used to store the images from the camera. Now on the back, I used the Bubble app on my iPod to receive the angle values. Lastly, the whole module is powered by a free portable battery. Remote sensing is perceiving without touching. For instance, all the way across the room, this dog perceives that a ball is in front of him. Now in engineering, remote sensing is implementing a device that perceives information from its surroundings. Sometimes it transmits a signal and other times it does not. This difference is known as active and passive sensing. Active sensing both transmits the signal and receives it, while passive sensing only receives the signal. In any event, it never physically comes into contact with the object. A dog would never have the restraint to do this. LiDAR is just one of the many applications for remote sensing. It specifically transmits and receives photons as its signal. When an object is encountered, a photon will deflect off of it and scatter, picked up again by the receiver. Understanding the speed of light and time interval between transmitting and receiving the photons allows the user to know the distance to the disturbance. When enough disturbances are received and the angles are known, a 3D point cloud can be generated that resembles the object of interference, in this case, the ball. For our LiDAR modules, rather than receive individual photons and then detect the distance given a time interval, we use computer vision through Python. Because our receiver is a camera which detects information and stores it as images, computer vision allows us to analyze every pixel in an image and teach a computer to make sense of it. The code that Dr. Mitchell provided to us searched images for the red line laser and used that image and varying offsets to identify distances from the LiDAR set up to the object. All this data was then acquired and integrated into one 3D point cloud. Calibrating the device required a lot of data collection. First, we used a green dot laser and the camera to take various images at different distances, ranging from 6 inches to 10 feet. As you can observe in this video, the further the target is away from the device, the closer the laser dot gets to the center of the image. This effect allows us to acquire coordinate values at these varying distances. The same process was performed for the line laser configuration, only this time, hundreds of points were being collected for every image rather than just one. To run the script, the Pi would ask for a distance from the wall. The user would be shown the image and could then verify that the data was acceptable. For the data acquisition, I went to my target to begin mapping. A Python script was written to receive angle values of the LiDAR module. It cannot be seen, but I am sitting in front of my laptop that is remotely connected to the LiDAR device using the VNC. With the computer set up, I then took a measurement to acknowledge the distance from the LiDAR module to the bookhouse. This measurement is not completely necessary, but it helps significantly to stitch together the sides of the 3D point cloud. And now, here's a video of the complete data acquisition for this front side. Data acquisition was not without its challenges. I already discussed a couple in this video, but here are a couple more. First, there's a lot of lighting in the back, and also with cars. Some are disguised as the laser, and so I had to remove that data. Second, there was a lot of light on the right side, and it actually showed up as red in the camera, and so it created a lot of false points as well. I also couldn't collect data from this because of the other bookcase was so close. And lastly, the ground was a little uneven, and so I had to end up rotating some of the 3D point clouds. So before we were collecting all sorts of data, and it came in the form of these test results, which show all these different points, and there's so many 000 values. And so the first thing I wanted to do is filter out all these 000 values and speed up the process of um, creating the 3D point cloud from the data. And so if you look at the program that I have, the first thing I do is I say if the words just being the line of text, I could have changed that value, but if that equals 000, then we're not going to deal with it. So we're going to get rid of it. So that's through opening, I have one called back, one called front, and one called left.txt. And the one that I use for the left, I'm also flipping to the right side because it's actually the exact same form. And so that actually worked out really well. And again, that's going to be a read file. But the one that I open, I have it as an append file. And I called that new.txt. So what I do is, as soon as we filter out the 000s, that eliminates so many different points right then and there. And then we have these XYZ values. And so I had to translate into floats from the strings, and then from the matrix that is given up here, or that is collected right here through this line split, I'm able to pull the different information and add little offsets for the translation. I'm really happy with how it looks. Right here you can see the stand, and it comes up into like a tripod kind of shape, and I don't need to show you, I'll show you that real quick. But yeah, it comes up in this like tripod shape, so even that shows up, which is really cool. And I could even get more detail on that if I took time to model it from the underside, and then I could get the base of this structure as well. And lastly, here is the final 3D point cloud overlapped on the actual object that I mapped. As you can see, a lot of the points actually really complete the bookcase, and I think it's actually a really good representation. You can see the stand, you can see the bookcase, you can see inside the window, and you can see the roof really well, and even the overhangs. Lastly, using Cloud Compare and not Mesh Lab, I was able to get a pretty decent final mesh for the project. So I did it two different ways. One, I just followed a YouTube video, and another, a friend instructed me on how to do it. And I'm really happy with how each of them turned out. But as you can see, there are a lot of holes on the two of them. And so actually I was able to overlap them, and actually they kind of complete each other and they fill those holes. And actually I'm very happy with the mesh. And the next step would be to put this into an STL form and then to 3D print it, but I haven't gotten around to doing that.